Hey there, guys. Good morning. Today's problem wants us to find the moment of inertia of a solid cone. And there's only three things about the cone that are provided: its mass, its height, and the radius of its base. Now, that doesn't seem like a whole lot to work with, but it's actually all that we need. I'll show you how it's done. Usually with these kinds of problems, the trick is to find another kind of shape that you could use to assemble the larger shape that's been given. And the reason you would want to do that is because it's way easier to deal with geometry that you're familiar with rather than trying to tackle a completely new shape all at once. In this case, since the base is circular, we could use the shape of a disc to recreate this cone. And that works out really nicely because we know a lot about discs already. So let's begin by cutting an infinitely thin slice from this cone in the shape of a disc, like that. The radius of that disc slice will depend on where we cut. If the slice is really close to the bottom, well, then the radius will be really small, and vice versa for a cut closer to the top. This means that an arbitrary slice of the cone, located anywhere along the middle, will have a radius of r as a function of its height, z. And since it's infinitely thin, we can label the thickness of the disk as dz, which just means a really tiny change in the height, z. This infinitely thin slice will contain an infinitely small amount of the cone's mass, which is just dm. So what we want to do here is figure out the expression for the moment of inertia of a disk slice, because as you can see here, the cone can be represented by a bunch of these disks stacked on top of one another, kind of like what I mentioned before. And we can take this idea a little bit further using calculus, where we can craft an integral of a bunch of infinitely small moments of inertia of those disks and sum it from the bottom of the cone all the way up to the top, and the result of that integral will be equal to the moment of inertia of the whole cone. So hopefully it's clear what we're trying to do here. Our next step will be to build an expression for an infinitely small moment of inertia of a disk slice, which is this di quantity here. To get that, we can use the regular disk moment of inertia equation as a starting point. And we've seen that plenty of times now. It's just 1/2 mr squared. But we need to change it up a little bit. Our infinitely thin disk doesn't contain the entire cone's mass. It just has an infinitely small chunk of it. So we'll have to switch out capital M in this expression for dm. And like I mentioned before, our disk doesn't have a single constant radius of r. Instead, it has a radius that gets bigger as you move upwards from the bottom of the cone. So we'll need to switch out r for r as a function of z as well. So this would be the proper representation for di. And we're going to take this and insert it into our integral equation. And before continuing, let's fix this up a bit. For one, the constant of 1/2 can get factored out. We don't need to leave that in there. Next, the integrand looks a little backwards right now, with dm listed first. Additionally, there's no need for these parentheses around dm anymore, so we can get rid of those too. If we fix those things up, here's what it looks like. So this is the integral that we ultimately need to solve. But I have some bad news. We can't even get started yet because there's two things currently standing in our way. The first is this integration variable. Remember, the plan is to integrate all of these tiny moments of inertia along the z-axis from the bottom of the cone to the top. So that means the integration variable needs to be with respect to z, not m. So we need to find a way to convert dm into something that contains dz. Secondly, this radius as a function of z also causes us some trouble. We need a proper definition for it that actually contains the variable z, not some other variable as a function of z. That's not even helpful here. We can't do anything with that. So until we get these two things out of the way, we can't move forward. Let's deal with the integration variable piece first, since that's a little easier to tackle. We know that the density of our cone is the ratio of its mass to its volume. And the density of a disk slice is defined similarly, except we're using infinitely small amounts in our ratio. But there's something very special about the density of the disk slice. It actually has the same density as the cone. Now, how do we know that? Well, if you take a chunk out of something that has a uniform density, then the chunk will contain the same density as well. It's really that straightforward. So, rho cone and rho disk slice are the same value, and there's no need to even use these subscripts. We can just write rho, regardless of what density we're referring to. So let me rewrite those like this. Now here's how this information is going to help us. I'm going to multiply both sides of the second line on this slide by the infinitely small volume of our disk slice, dV, like that. Let's go one step further and replace dV with its definition. And what would that be? Well, the volume of a regular disk is pi r squared times its height, or its thickness, whatever you want to call that. The volume of our disk slice will be similar, except we would have to replace r with r as a function of z and dz as the height. Okay, cool. Look at that. Now we're getting somewhere. dm is equal to this expression that contains dz, just like we wanted. Awesome. Let's go back to our integral and substitute this in for where we had dm. From here, we can factor out the density and pi, since those are constant, and we can remove the extra parentheses, since they're no longer needed. The product of these two r as a function of z quantities in the integrand will combine to a single quantity raised to the fourth power. And now we're ready to fix the remaining issue. And for that, we're going to have to focus on our picture. Within the geometry of our cone are some hidden triangles that can help us out. Here's one of the triangles that spans the entire length of the cone. Let's go ahead and grab that and move it off to the side, and we will just label it for now. For the second triangle, we'll need to draw one in the same shape as this purple triangle, but with a height of z instead, where, remember, z represents any height value between the top and the bottom of the cone. And we saw how for any height in the middle of the cone, the radius is r as a function of z. So once your triangle is drawn, move it over and put those quantities in for the height and the radius. Now, take a look at this. We have similar triangles going on here. And in case you're wondering how we know that, take a closer look. They both share a right angle in the same spot. And the bottom angle is drawn from the same vertex point on the cone. Plus, the hypotenuse of both triangles has the same slope, since that's representing the slant of the cone. Therefore, the bottom angles between these two have to be the same as well. So if this angle is the same as this angle, and this angle is the same as this angle, well, in order for both triangles to add up to 180 degrees, these remaining angles have to be the same as well. And we have two similar triangles. Thus, the ratio of the two known sides of one triangle, r over h, is equal to the ratio of the two known sides of the other one, r as a function of z over z. And we can use this to solve for the definition of the radius as a function of z by just multiplying both sides by z. And there it is. So let's take this and go back to our integral, and we're going to plug in the expression that we just obtained, like that, and then raise it to the fourth power. The radius of the base of the cone, which is capital R, is a constant, and so is the height of the cone. So both of those quantities raised to the fourth power can be factored out, like this. And here's what's left. Now, isn't that nice? That's super easy to integrate. We can use the power rule of integration, which means we're going to increase the exponent by 1 to 5, and then divide z to the fifth by 5, okay, like this. And evaluating at the endpoints is super easy too, since one of them is just 0. So all we have to do is just plug in h for z, and here's what we get. So we have h to the fifth in the numerator and h to the fourth in the denominator. So those two will end up canceling each other out, and they will leave a single h left over upstairs. And the 2 and the 5 downstairs will multiply together, resulting in 10. And here's what we get. Sweet. So does this mean that we're done? Well, no, it doesn't, unfortunately. But we're just about there. Let's go through these variables and verify which ones that we know. We were given h, so we definitely know that, and the same applies to capital R. We don't know the density, however. If we substitute in the definition for the density, which is just the mass of the cone divided by its volume, well, we were actually given the mass, right? So really, the only thing that's currently standing in our way is the volume of the cone. Here's what we should do. Let's grab the equation for the volume of a right circular cone. And here's a reminder of it, in case you don't know. We should take this expression here and plug that in for v and see what we end up with. If it's going to be a moment of inertia result, it should probably be in the form of some kind of a number times mr squared. So let's see if that's what we get. As a helpful intermediary step, let's go ahead and take m over v and pull it down in front, like this. When we do that, it should be clear what's ending up in the numerator and the denominator once we're done canceling things out. We're not actually changing the expression or anything. This is just for the sake of clarity. So let's go ahead and substitute that expression in for v, like this. And to make it a little bit easier, instead of dividing m by a fraction, let's multiply m by that fraction's inverse. Now it's super clear what's going to cancel out with what. Let's see. The pi's will cancel each other out, and so will the heights. And 2 factors of r upstairs cancel out the 2 that are downstairs, leaving just 2 remaining. And boom, here's what we end up with. 3/10 mr squared. And that is exactly what we expected for the form of moment of inertia. And the solution manual agrees. So this is our answer. I hope that this helped. Thanks for watching, folks. Have a good one.